This is Amy Woodman, dietetic intern from the University of St. Joseph, with a journal review of a study by Joseph Zacular et al. Titled Dietary Zinc Alters the Microbiota and Decreases Resistance to Clostridium difficile infection. This is a rather complex study consisting of several mouse experiments, one in vitro experiment, and 2 human studies. And I'd like to just start out with a little bit of background before we get into the study itself. The human microbiome has been a topic of intense interest of late, not only to dietitians, but across multiple disciplines as we find out just what an impact the microbiota have on human health. At the Food and Nutrition Conference and Expo in 2016, Joanna Lempe and Colleen Webb made an interesting point in their talk, Feeding the Gut Microbiome. They distinguished between the two terms microbiota and microbiome. And these terms are often used interchangeably, but they do refer to specifically different things. The microbiota is the population of microorganisms living within our gut, and the microbiome refers to the genetic material contained within this population. This is a slide presented in that same talk. It's from the journal Nature, and it's data from the Human Microbiome Project. And when you look at the top bar represents the microbiota. Each point along the x-axis is an individual human subject with their relative quantity of each of the phyla represented in their microbiota. And when you look at the bottom figure, this is the microbiome, and each color bar represents the gene expression of each metabolic pathway listed on the right. And you can see, well, there's quite a lot of variation within the microbiota. When you look at the microbiome, there's less variation. It becomes a little more consistent. So I think this is important to remember, since the terms are often used interchangeably, but that they do refer to specifically different things. And it's also important to keep in mind as more research regarding the microbiome is going to be coming out, just to keep this difference in mind. Clostridium difficile is a common cause of antibiotic-associated diarrhea. It accounts for 15 to 25% of all cases. Patients present with fever, pain, decreased appetite, diarrhea, and nausea. It's very easily spread and most common in the elderly patients, patients receiving antibiotics or proton pump inhibitors, and also with patients with long lengths of stay. These are some of the most recently available statistics from the CDC, and in 2013 there was a 10% decrease observed in hospital-acquired infections, but it still is a prevalent cause for antibiotic-associated diarrhea in the clinical setting. Calprotectin is a zinc-binding protein that was discussed at length in this study. It's a cytosolic protein found in neutrophils, and in human studies, elevated levels have been observed in all causes of diarrhea and colonic inflammation. Calprotectin can be easily measured in plasma and fecal samples, and it's also present in other bodily fluid samples such as saliva, urine, cerebrospinal fluid. And the literature consistently shows that elevated levels in humans show a strong correlation with colorectal inflammation of all causes. This study investigates the role of zinc in C. diff infections. The most common indicator for zinc supplementation in a clinical setting is for patients who have poor oral intake and non-healing pressure ulcers. The typical dose is 220 milligrams of zinc sulfate for 14 days. And zinc is involved in several wound healing processes, including epithelialization, collagen deposition, and cross-linking, as well as fibroblast proliferation. This study consisted of a series of mouse experiments. Each experiment was repeated twice with at least 5 mice in each group. There was also 1 in vitro experiment, as well as 2 small human retrospective studies. In the first experiment, mice were divided into 3 groups and fed diets with varying amounts of zinc. The first group was fed a diet containing 0 milligrams of zinc per kilogram of feed. The control group was fed 29 milligrams of zinc per kilogram of feed, which is the standard amount of zinc in mouse feeds used for laboratory animals. And the experimental group received 1,000 milligrams of zinc per kilogram of feed. And they wanted to establish that the elevated levels of zinc would indeed have an impact on cecal and colonic zinc content, and they did find that. They wanted to eliminate any signs of toxicity that would confound later results, and no signs of toxicity were observed in the mice receiving the experimental diet. But what they did find that the mice fed the high zinc diet had a marked decrease in bacterial diversity. They had a decrease in Clostridium and Enterobacter and an increase in Enterococcus. And this change was observed relatively quickly after just 1 week of receiving the high zinc diet. And there was no change observed in bacterial burden. Next, they wanted to investigate the impact of the high zinc diet on C. diff infection. The standard protocol for inducing C. diff in mouse populations is to administer a solution of 0.5 mg per ml cephalosporin followed by an oral dose of C. diff spores. And after they did this, they found the mice fed the high zinc diet had an increased severity of infection. They showed increased inflammation, increased damage to the GI epithelium, as well as pseudomembrane formation. There was no significant increase in C. diff burden, but the mice fed the high zinc diet did have increased C. diff toxin titers, as well as increased pro-inflammatory cytokines and decreased anti-inflammatory cytokines. There was also a decreased barrier function for the mice fed the experimental diet, and they were able to observe a translocation in GI bacteria in the liver tissue of the mice on the experimental diet. Next, the authors investigated whether or not zinc had an impact on the antibiotic threshold for induction of the C. diff infection. So mice were treated with a solution of cephalosporin 50 times less concentrated than the standard. So instead of using 0.5 mg per ml, they used 0.01 mg per ml. And what they found was when they induced the C. diff infection, only the mice on the high zinc diet developed a C. diff infection. They showed a more severe infection and a decrease, as well as a decrease in diversity of their microbiota. And the mice on the controlled diet, as well as the 0 zinc diet, maintained their microbial diversity. Next, the authors conducted some experiments with calprotectin deficient mice. These are mice genetically engineered to be deficient in the calprotectin protein. And as they expected, these mice, when they were induced with C. diff infection, had decreased survival and increased severity of disease. Next, they took calprotectin deficient mice and deprived them of dietary zinc for 5 weeks prior to inducing C. diff infection. And when they did this, the mice showed a decreased severity of disease. And this further illustrates that the mechanism here is zinc dependent, and whether it's calprotectin binding the zinc or mice being deprived of dietary zinc, the mechanism is that making the zinc unavailable to the microbiota is what's causing the change in the severity of infection. The in vitro studies further illustrated the role that zinc plays with C. diff infection. When C. diff was grown in culture, the growth was inhibited by adding calprotectin. The addition of zinc reversed this effect, so thereby showing that C. diff requires the presence of zinc to grow both in vitro and in the mouse populations. When the authors added recombinant calprotectin that was deficient in its zinc binding properties, that did not inhibit the growth of C. diff in vitro. There were 2 retrospective human studies done, and although they're small in scope, they are consistent with the available literature on calprotectin and C. diff infections in humans. The first study involves 25 pediatric subjects with C. diff infections, and they looked at fecal calprotectin levels, and what they found was that increased fecal calprotectin was associated with more severe C. diff infection in pediatrics. Next, they looked at 48 adult subjects with C. diff infections, and they looked at the serum calprotectin levels in these subjects, and they found the same, that increased serum calprotectin was associated with increased severity of C. diff infection. Conclusions that can be drawn from this study: dietary zinc does have an impact on gut microbiota in mouse populations. Increased dietary zinc lowers the amount of antibiotic needed to induce C. diff infection in mouse populations. Increased levels of dietary zinc increase the severity of C. diff infection in mouse subjects. And calprotectin can limit severity of C. diff infection in mice by binding zinc and making it unavailable to the gut microbiota as well as the C. diff. So what does this mean for us? Can these results be generalized to human populations? What impact do zinc and calprotectin have in human subjects? A review of the literature shows a strong correlation between elevated serum and fecal calprotectin levels and increased severity of all-cause diarrhea and colon inflammation in human subjects. So further research would be required to determine the impact of dietary zinc in human patients. Perhaps a retrospective study which looked at the incidence of C. diff in patients who received zinc supplementation compared to those who did not receive supplementation would be helpful in determining the role of dietary zinc in human patients. Another inconsistency with this study is with the amount of zinc that was used for the experimental group. The mice received 1,000 milligrams of zinc per kilogram of feed for 5 weeks, and the authors stated this was meant to simulate excess supplementation in humans. This represents 34 times the amount of zinc in the standard mouse chow, and in a clinical setting, a patient is very unlikely to ever receive this much zinc. And just to compare, I created a hypothetical patient, and I grossly overestimated how much zinc they would receive, and I allowed for the patient to receive the entire daily value, 15 milligrams of zinc from their oral intake. I suppose that they would receive 2 Ensure supplements, giving 8 milligrams per day, a multivitamin with 15 milligrams of zinc, and a zinc 220 milligrams of zinc sulfate, which would yield 51 milligrams of elemental zinc. And if you total all this up, it would bring you to 89 milligrams of zinc, which is still 6 times the daily value, but really not even close to the amount that they used in this mouse study, which was 35 times the standard amount. So it's very unlikely that patients would get this much zinc in a clinical setting, and the mice also received this amount of zinc for 5 weeks, whereas we would usually supplement with the zinc sulfate for only 2 weeks. While this study is not generalizable to human populations for the aforementioned reasons, it was a very well-designed study. The authors thoroughly investigated and defined the mechanism of action of the calprotectin binding the zinc and the resultant effect on the microbiota, as well as the C. diff infection severity. The study earned a positive rating on the quality criteria checklist from the Academy of Nutrition and Dietetics. One of the drawbacks of this study was that they were not able to blind the study out of concern for cross-contamination of the various types of mouse feed that were used. There were no financial disclosures by any of the authors, and bias was unlikely as the study was funded by the United States National Institutes of Health, the United States Department of Veterans Affairs, as well as the Vanderbilt Digestive Disease Research Center. So it's unlikely that there will be any bias, any source of bias in this study. Thank you for listening. I hope you found this journal review to be informative.